Swayam Prabha. Digital India. Educated India.
Good morning, everyone. Welcome to Introduction to Electronics class. This is class number 6. So far, we have covered semiconductor diode, and also we have covered different diode applications. Today, we are starting a new chapter, which is BJT, or bipolar junction transistor. Let me share the slides with you. So we are starting bipolar junction transistor today. It is, in short, it is known as BJT. Okay. As the name suggests, this particular device is an active device. It carries both electrons and holes. So that is why the name bipolar has come. The BJT was invented in Bell Labs, okay, in US. First at the end of 1947 by John Bardeen and Walter Brattain. This was a point contact device using germanium, whereas William Shockley developed the BJT device that was and explained this working principle beginning of 1948. Okay, that was not point contact, that was like PN junction kind of BJT device which we have, which we use today. Okay, for this discovery, for this invention, Bardeen, Brattain and Shockley, they received a Nobel Prize in 1956. Okay, now this is a very important device. We will see in our discussion. We will mention about its two applications. One is an application as an amplifier, okay, and application as switch. Now, what is amplifier? That we will discuss in more detail much later on in the next chapter. But let me briefly tell you, if I apply an input signal in an amplifier, okay, in an amplifier block, then what will happen? It will basically the signal at the output we will get is the amplitude will be much more than of that of the input signal. So that is basically an amplifier. Okay, there are other properties which we will discuss later on, but if we want to amplify the signal, we need amplifier, and BJT can act as an amplifier circuit. Okay, what about switch? Switch we have come across before when we are discussing diode, but in case of switch, as you know, that switch can be on and off. If the switch is off, current through the switch is 0, okay, and entire voltage will be across the switch. Whereas when the switch is on, okay, the current is maximum, and the voltage current is maximum through the switch, and voltage across the switch is basically 0. So BJT we can apply, we can have both this amplifier application and the switch application. Okay, that we will see later on as the course progresses. But let's discuss first what is the structure of BJT and what is its working principle. Okay. As I mentioned, bipolar junction transistor was named because its operation involves conduction of two carriers, electrons, and two types of carriers, electrons and holes. So this is the symbol of BJT. BJT can be NPN type or it can be PNP type. Okay. So you see there are three semiconducting region, two sides N region, and in between that N region there is a P region. So this P region is sandwiched between 2n side or 2n regions. Okay, it is a 3-terminal device. So one terminal is known as emitter, another terminal is known as base, and the third terminal is known as collector. So base is sandwiched between emitter and collector. Okay, so this is an NPN transistor because emitter is N type, collector is N type, whereas this base is P type, which is sandwiched between 2N. So it is known as NPN BJT. What about PNP BJT? As the name suggests, here emitter and collector is made of P, okay, whereas the base is made of N. So base is sandwiched between, again here also emitter and collector, and but base is N type and emitter and collector is P type. So PNP BJT. Okay. Now this is the typical BJT symbol. You see this emitter, base, and collector. There is an arrow always on the emitter side, and arrow represents the direction of the current. Arrow represents the direction of current. Okay. Um, Here also PNP, in case of PNP BJT, the symbol is like this. Here also arrow you see on the emitter side, but the current is entering, so the direction of arrow is like this. Whereas in case of NPN, the current is coming out from the emitter, so that the arrow direction is like this. Okay. So that is what I mentioned. The symbol of BJT includes an arrow for the emitter terminal. Its direction indicates the direction of the direction when the transistor is in the active mode, direction of current. Okay. Now, so you see in BJT there are two junctions. This is one junction, and this is another junction here. Similarly, there is one junction here, and this is another junction here. So let me, base emitter junction, BE, this is base and base emitter junction, and this is base collector junction. Similarly, this is base emitter junction, this is base collector junction. So this is a 2-junction device, but 3-terminal device, right? Let's discuss it a bit more about the structure. Okay. As I said, it is a 3-layer semiconductor where base is sandwiched between emitter and collector. That is already we have mentioned. If you see carefully, it is like two back-to-back diodes. Okay. So you see one diode is this, another diode is this. Two diodes. Here also one diode is this, another diode is this. Okay. So two diodes are there, two back-to-back diode, and however, if you buy two diodes from the market and connect it like this, it will not act as a BJT. Okay, simply because the base region is much thinner, okay, compared to emitter and collector. So if you just buy two diodes and connect them, it will not act as a BJT. That we will discuss in a minute. But the primary reason is the base region is much thinner compared to emitter and collector. Okay. That is what I tried to mention here. But even if the base is thinner, we have to make sure that the two depletion region at the two junctions should not touch each other. So if I try to draw, so we have emitter, base, and collector. Okay. So There is depletion region here in this junction. There is also depletion region in this junction. So if we make this base region very thin, then two depletion region might touch each other. Okay, that is known as punch through. Okay, so we have to make sure, even if we are making this base very thin, the depletion region from both sides shouldn't touch each other. Okay, that is I tried to mention here. Uh, Now, as far as the doping concentration is concerned, emitter is the highly doped, highest doping concentration, and collector has least doping concentration. Okay, and base is in the middle, as far as the doping concentration is concerned. Um, the area is maximum for the collector and minimum for the base. Okay, and the collector maximum ensures that collection of all the carriers crossing from base. Okay, that we will see in a minute. And base is the minimum, ensures that most carriers, so carriers in when they travel from emitter to collector, the less width of the base ensures that most of the carriers go from emitter to collector. Okay, without recombining at the base region. So that's the whole purpose of making base much thinner. Okay. Mm, and BJT with two PN junction that we have already talked about, but therefore there are four possible modes of operation of BJT. Okay, because there are two PN junctions, we will see what are the four modes in a few minutes. Now, first see whether whatever I have discussed so far, that this two back diode, if I buy two back-to-back diode and connect it to form a BJT, it will not act as a BJT. Okay, so you see that we will discuss. Okay, so this is an NPN BJT. You see, this is emitter, this is base, and this is collector. Okay, these are all metal contacts. You need to take metal contacts so that you can take take contact of those terminals. Okay, um, um, so BJT is not symmetric, you see, which is because the doping concentration is different, and also the area wise they are different. So we can't use, although they are NPN, we can't use collector as emitter and emitter as collector. See, okay, so it is not a symmetric device. Now, so this is this is I just mentioned to you before. BJT can't be used as two back-to-back diode. Okay, although there are two junctions here, we can't just buy a PN two two diode and form a BJT. Okay, so that is I have drawn here. So one diode D1 and D2. Okay, it is possible to show this D2 will act as a constant current source. That you will understand when we will discuss the BJT characteristics, particularly BJT output characteristics. Anyway, what I want to point out, if you buy two diodes and connect them back to back, then it will be like this. Okay, P, N and P, whereas the actual BJT structure is like this, where this base is, as I mentioned, is much thinner, okay, compared to emitter and collector. So a BJT is not the same as two diodes connected back to back. Okay. So as I mentioned to you that there are two diodes, so two PN junctions. So four possibilities are there. One junction is known as BE junction, that is base emitter junction. Okay, and the other junction is base collector junction, BC junction. Okay, so this base emitter and base collector junction. So if I talk about NPN BJT, NPN and emitter, base and collector. Um, So this is my base emitter junction. This junction can be forward bias and reverse bias. So as the base collector junction, this junction can be forward bias and reverse bias. So I have written here. So emitter bias junction can be forward bias and reverse bias. The base collector junction is also can be forward bias and reverse bias. And depending on which junction is biased in which way, the application of BJT depends. Okay. For example, if the BE junction is forward bias and BC junction is reverse bias, we will have a region or mode of operation known as forward active region. Okay, in this region is very important to realize BJT as an amplifier, that we will see later on. Okay, but as base emitter junction is forward bias and base collector junction is reverse bias, this particular region is known as forward active region. Okay, when both these junction is forward bias, when both BE and BC junction is forward bias, this is known as saturation region. Okay, whereas when base emitter junction is reverse bias and base collector junction is reverse bias, both the junction is reverse bias, in that case it is in cutoff region, the BJT. Okay, and in the so forward bias and reverse bias. Okay, base emitter forward and base collector reverse bias, forward active region, both of them forward bias saturation region, both of them reverse bias cutoff region. If it is opposite to that of the forward active region, that means base collector junction is forward bias, whereas base emitter junction is reverse bias. It is known as reverse active region. This is opposite to forward active region. Okay, so these are the four regions. We will mainly concentrate on forward active region, saturation region, and cutoff region. Okay, and forward active region is usually used in case of amplifier, whereas saturation region and cutoff region is used in case of when BJT is used as a switch. Okay, now let's discuss this forward active region or forward active mode in more detail, because that will give you the that will help us to understand how this device works. Okay, so this is the left hand one is NPN transistor. Okay, this is the NPN transistor or NPN BJT. In case of forward active mode, we said that base emitter is forward bias and base collector is reverse bias, right? So if this is my emitter terminal and this is my base terminal, these two will be forward bias if we connect the negative supply of the battery to N and positive supply of the battery to P. Okay, this is obvious. Negative supply is connected to N, positive supply is connected to P. That means this particular junction, BE junction, is forward bias. Okay, similarly this is my collector. Okay, and this is my base. So collector is N type and base is P type, right, in this particular example. So you see this junction will be, this base collector junction will be reverse bias if this collector is connected to positive supply of the battery and base is connected to negative supply of the battery. That means this is reverse bias. Okay, so base collector is reverse bias and base emitter is, so this is my forward bias junction and this is my reverse bias junction, right? You remember in case of forward bias, when the junction is forward bias, the current in the junction of a diode is basically exponential. You remember diode current characteristics. So I have a PN junction. Forward bias means if it is silicon diode more than 0.7 volt, then current will exponentially increase, right? Whereas if the diode is in reverse bias, current is there is hardly any current. Okay, that current is basically reverse leakage current. You remember that is around a nanoamp to picoamp. Okay, so Even it can goes to below picoamp and femtoamp also. Okay, depending on the diode doping and area and all that. So now, when this base emitter junction is forward bias, that means electrons from N will enter to base, right? And holes from base will enter to emitter, correct? Because both are majority carriers. Electron from N to reach go to base, and holes from base will go to emitter, right? So that is what it is shown. This white line is holes and this gray line is electrons. Now, as base is very tiny, okay, most of the electrons which will come to the base, they will be able to reach to the collector, okay, because they will see this positive supply of the battery and they will basically dragged by this positive supply of the battery. Some part of the electron, very few, will recombine with holes in the base. Okay, that happens in the p-n junction, right? If I draw a p-n junction, you remember. So this is my n, this is my p. So electron, when they cross here, they basically exponentially their concentration goes down because they recombine with holes. Similarly, the holes crosses this junction, they also exponentially goes down because they recombine with electrons. So that this recombination part is known to you, right? But what is not known is lots of electron will not recombine because this base region is very tiny. Okay, this base region say finishes here, so lots of electrons are there. Not electron level not goes down. Lots of electrons are already there. They couldn't recombine. Okay, and they will see this positive supply of the battery, and they manage to reach to the collector. Okay. Similarly, if we talk about PNP transistor, this base emitter junction, this is my base emitter junction, like the first one, is forward bias. That means this positive supply is connected to P, and this negative polarity of the supply is connected to N. Okay, so that is forward bias. What about the base collector junction? Base collector junction, here it is in reverse bias because this P is connected to negative supply of the battery and N is connected to positive supply of the battery. Okay, so they are in the so this base collector junction is reverse bias. Okay, and this base emitter junction is forward bias. So, but in case of PNP transistor, holes from P goes to the base, that is N region. Okay, and electrons from N go to the P region, that is emitter. Electrons from N, that is base, go to the N region. These holes which will go to the base region, most of them manage to go to the collector. Okay, and very few of them recombine with the electrons in the base. Okay, simply because they will certainly not get time to recombine because the base region is so tiny. Okay, most of them will reach to the collector. Now this because the reason they will reach to the collector, as I said, they will see this negative terminal of the battery and they will be dragged, the holes will be dragged by this negative terminal of the battery and reach the collector. Okay. The one point I would like to mention, compared to NPN, in case of PNP, the current direction are reversed. Okay, and voltage subscript are also switched. So let me, sorry. So what I try to say is, you see, as electrons are moving from left to right here, the current direction is opposite, right? In direction of the motion, the direction of electron and current direction is opposite. So current is going out of the emitter. Okay, here current is entering to the base, because hole, direction of movement of hole you see, and here also current direction is, current is entering to collector. Okay, so current is entering at collector and base, and current is coming out from emitter. Okay, so if you remember your NPN symbol, your NPN symbol was like this. In the few slides ago I have shown the NPN symbol, okay, of the transistor. You will see that this arrow is going out, so that is current is going out here. So that is why this is my emitter, this is my base, and this is my collector. So the arrow will always on emitter, and it represents the direction of current, and current is coming out. What about here? Here holes are basically going from left to right. That means the current is going from left to right. So the current is entering to the emitter. Okay, electron movement is this way. That means current is coming out from the base, and current is coming out from the collector. Okay, so in case of PNP transistor, the direction of current is, if this is my emitter, this is my base, and this is my collector, direction of current is entering from the emitter side. Okay, so current direction is reversed compared to NPN. In PNP the current direction is reversed, and also voltage subscript needs to switched. Okay, so here we are saying VBE and VCB. Here we usually say VEB and VBC. Okay, so that's basically the convention. Basically you represent, you give, so BE means B, the one you give first, which contains the positive of the battery. Okay, base contains the positive, so BBE. VCB because collector contains the positive, okay, of the battery. VCB. Here also VEB because the positive of the battery is connected to emitter. Here VBC because the positive of the battery is connected to base. Okay, I hope this is understandable. So two external voltages, voltage source set the bias condition of the active mode. Okay, in forward active mode, as I mentioned already, base emitter will be forward bias and base collector will be reverse bias. Okay, so that is I have written here. B junction is forward bias, and CB junction or BC junction will be reverse bias. Okay, now let's discuss the BJT currents. Okay, what are the currents? That I have already discussed, but let's explain it in more detail. So there are three currents as already mentioned. One is emitter current, one is base current, and one is collector current. Okay, so we can write IE is equal to IB plus IC. That is true for both NPN and PNP transistor. Okay, as base emitter junction is forward bias, as I already mentioned, the current through this junction is exponential function of base emitter voltage. So IE can be written as exponential VPE over VT. That we know from our diode classes, right? The diode current is proportional to exponential VBE over VT, right? That is the base emitter voltage, and VT is the thermal voltage, that is close to 26 millivolt at room temperature. So IE as base emitter junction is forward bias, the IE is proportional to exponential VBE over VT. Okay. What about the base current? Base current, if you look carefully, base current has two components. One is because say for NPN transistor, okay, base current is because these holes from base is entering to emitter, so that will generate one base current, which we are saying IB1, and another base current is IB2, where this holes is basically recombining with some of the electrons. That number is few because base width is tiny, but there will be current, base current, because of this recombination. So base current has two parts. One is some holes cross this junction because this junction is forward bias, and the other part is some holes will recombining with electrons. Okay, so this is I have written here, holes from base will go to emitter because base emitter junction is forward bias. Okay, go to emitter, that is IB1, and a few electrons will recombine with holes. Okay, and gives rise to another base current. Okay, IB2. This is known as, obviously known as recombination current, because it depends on the on how many electrons and holes are recombining. Okay, and this recombination current of course depends on number of electrons injected from the emitter. Okay, so if you think carefully, the base current, total base current, is also proportional to exponential VB over VT, total base current. Why it is so? Because you see this IB1 of course depends on exponential VB over VT, because the IB1 base emitter junction is forward bias. Okay, base emitter junction is forward bias. Base emitter junction is forward bias. Okay, now this what about the what about this component? This component, as it depends on electrons injected from emitter. Okay, number of electrons injected from emitter. So more the number of electrons injected from emitter, more will be the recombination. Okay, recombination current. So you see this number of electrons injected depends on the exponential VBE. Okay, so overall this base current it depends on exponential VBE over VT. What about the collector current? The collector current is basically the electrons crossing the base collector junction, right? That gives rise to collector current. You see, sorry. So collector current is number of electrons crossing this junction. Okay, so the more the number of electrons crossing the junction, more will be the collector current, and this number of electrons crossing the junction depends on how many electrons crossing this base emitter junction. In other words, these collector currents basically depends on the again the base emitter voltage. You see. Okay, so the electrons crossing the base collector junction gives rise to collector current. So this collector current is proportional to exponential VBE over VT, but independent of BC voltage. Okay, why I am saying this independent of BC voltage? Because you see if you look at the reverse bias of the base emitter reverse bias of any PN junction. Okay, this is the reverse bias region, right? You see this current here doesn't depends on this voltage, reverse voltage. You see this current is very tiny, reverse leakage current, but it is independent of the of this reverse voltage you are applying. Okay, so that is what we are saying, independent of BC voltage. This current is independent of BC voltage, because this BC voltage this voltage is reverse bias, right? So whatever voltage you are applying, this collector current doesn't depends on this voltage, because in reverse bias of the diode this current is basically independent of this reverse bias voltage, right? Now if we increase this, if we manage to increase this current, how we can increase this current? If somehow there is lots of carrier here, those carrier can be dragged or drifted by this supply voltage, then the amplitude of current will increase. But even then these currents is independent of the reverse bias voltage. Okay, what it depends on, how many carriers manage to cross this junction. Okay, so that is why I have mentioned here this the electrons crossing the base collector junction gives rise to collector current, and this collector current is proportional to exponential VBE over VT. Okay, but independent to base collector voltage, because base collector voltage is reverse bias. So to summarize, base current will be much smaller than the emitter or because why it is smaller? Because base doping is less. That base doping is less means your IB1 will be less. Okay, sorry. What about the second part, IB2? Base width is less. That is why IB2 is less, because the electrons, in case of NPN transistor, the electrons which manage to cross this emitter base junction, they will zip through the collector, zip through the base and go to the collector, simply because the base area is very tiny. Base is very thin, and almost all the electrons manage to reach the collector, and very few of them will recombine with the holes of the base. So that is why this IB2 will be less, and the reason being the base width is less. Okay, and another point is collector current is slightly smaller than the emitter current. Okay, this is because why collector current is slightly smaller than emitter current? Because some of the electrons will recombine at the base, right, and rest of the electron will reach to the collector. So obviously collector current will be slightly less than that of the emitter current. Okay, slightly less. In fact, we represents collector current as alpha IE, where alpha is close to 1, less than 1. Okay, alpha is close to 1 but less than 1. So thus the current at one terminal is controlled by the voltage across the other two terminals. This control is basic transistor action. This control, because this collector current is controlled by the base emitter voltage that is present in the other two terminals. So this is the heart of the operation of the BJT, or bipolar junction transistor. Now if I clear this slide now, so this will be the yeah, so just discuss the current relationships. Okay, we have mentioned that both in case of NPN and PNP, IE is equal to IB plus IC, right? That you can see from the arrow here. IE is equal to IB plus IC. If we just consider Kirchhoff's current law, we can write this. Similarly here also, IE, that is the current coming out from the emitter in case of NPN transistor, is sum of base current and collector current. Okay, now if transistor is biased in the forward active mode, we can write beta is equal to IC plus IB. IC is the collector current and IB is the base current, and they are linearly related, because you see IC is proportional to exponential VBE over VT. Okay, IB also proportional to exponential VBE over VT, right? So they are basically linearly related, and their ratio is usually represented as beta. Okay, so this beta of a transistor usually few hundreds. Okay, that also depends on what kind of transistor it is, but it's usually several hundreds. Okay, often few hundreds. Okay, so if you use this and this equation, we can write IE is equal to IB1 plus beta, and IC is equal to IC beta plus 1 by beta. That means we can represent IC is equal to alpha IE, because IC is close to IE, and value of alpha is just little bit less than 1, okay, and alpha can be written as beta by beta plus 1. Okay, beta by beta plus 1. So so to summarize, we have today we have discussed we have started an active semiconductor device known as bipolar junction transistor. It's the application like amplifier and as a switch we will discuss later on. Today we try to cover the structure of BJT. BJT is a three-terminal device. It has two junctions. One junction is known as base emitter and another junction is known as base collector. As BJT is a there are two junctions, so we can have like four different combinations of the way we can bias this junction, and we mentioned that if base emitter junction is forward bias and base collector junction is reverse bias, the BJT can act as an amplifier that we will discuss later on. And if both the junction is forward bias, BJT will act as a switch and this region is known as saturation region. And if both the junction acts as a reverse bias, then BJT will act as a switch also, but that is in the cutoff region. Okay, so one is saturation and one is cutoff. In both the region, BJT will act as a switch. One is switch on and another region it is switch off. Okay, so apart from that, we have also discussed NPN and PNP BJT, how the current flows, and there are three currents: emitter current, base current, and collector current. In case of NPN, the main current component is because of electron, and in case of PNP transistor, the main current component is because of holes. In case of this main current component is basically emitter current is proportional to exponential VB over VT, because the base emitter junction is usually forward bias in case of active region of BJT. And base current, as I mentioned to you, it has two components. One is IB1 and another is IB2. IB1 is because this is forward bias, and IB2 is because some part of the carriers, say in case of NPN, the electrons will recombine with holes. Okay, so these two is, you see, both these components is proportional to exponential VB over VT. What about the collector current? We mentioned the collector current also depends on the base emitter voltage, because the collector current is depends on the number of electrons managed to reach the collector. So and this number of electron is basically depends on exponential over VB over VT. So collector current is also proportional to exponential VB over VT. However, it is independent of base collector voltage, because base collector voltage is a reverse bias voltage. Okay, the point I mentioned that base current is amount of base current is very small, okay, or less, and the collector currents are slightly smaller than that of the emitter current, because there is little amount of recombination at the base. Okay, so with this we are basically closing the class today. In the next class we will discuss different modes of BJT operation, and probably we will start the biasing of the BJT. Okay, so with this I am closing this class. Thank you very much for your attention. Bye for now.